Bubble column reactors are widely used in the chemical process industries. In this presentation, I consider the operation of a bubble column in which the liquid phase is subjected to low frequency vibrations. Depending on the height of the column and the vibration frequency, the bubble column can operate in different harmonic modes. For example, this is the first harmonic, the second harmonic, third harmonic. The gas holdups along the height of the column is not uniform, but is the highest at the antinodes and is lower at the nodes of these harmonics. Overall, due to the application of low frequency vibration, the gas holdup in the column is enhanced significantly. And we examine the reasons behind the improvement in the gas liquid contacting due to the application of low frequency vibrations. For background material and the theory, I refer you to this publication in Chemical Engineering Science published in 2005. Bubbles produce an acoustic signal on formation and deformation. Let's listen to the sound of a waterfall. This is the sound of a wave. Bubbles also respond to a sound field, and that is the topic for discussion today. We begin by examining the influence of low frequency vibrations to the liquid phase on the hydrodynamics of a single bubble. We take a glass column and the liquid phase is connected to a vibration exciter. A single bubble is injected into the column by means of a syringe, and we use a high-speed camera in order to examine the influence of the vibration amplitude and frequency on the rise of a single bubble. We demonstrate that under certain conditions, the single bubble can be made to levitate or can be made to traverse downwards rather than upwards. Let's first examine what happens to a single bubble that is rises in a liquid that is subjected to vibration at a frequency that varies from 85 hertz to 100 hertz. The frequency is now increasing to 100 hertz, decreasing back to 85 hertz, increasing to 100 hertz again. So the bubble rises when the frequency increases, and the bubble descends when the frequency decreases. If, on the other hand, the liquid phase is subjected to a vibration at a constant frequency of 92 hertz, the bubble levitates. If we examine the close-up of the levitating bubble, we notice significant deformations in the bubble surface. Let's turn our attention to the influence of low frequency vibrations on bubble column operation. The experiments were carried out in a glass column, perspex column of 10 centimeter diameter. The liquid phase is vibrated with this vibration exciter. The details of the experimental setup are available in this publication. So this is the this is connected to the vibration exciter, and the liquid phase is subjected to vibrations, and above that we have a gas inlet where gas is injected through capillaries along the sides of the column. We take high-speed photographs of the bubble hydrodynamics with this high-speed camera, Fastcam Ultima 40K, and this can be zoomed in at various positions along the height of the column. Let's first look at an experiment, set of experiments, 4 in number, in which the gas holdup in the column is measured as a function of the superficial gas velocity, and in the 4 sets of experiments are shown by these different symbols here. The red circles are for an unvibrated column. The blue squares are for a column subjected to a vibration amplitude of 1 millimeter, and the liquid phase is vibrated at a frequency of 30 hertz. The green triangles are for a vibration frequency of 40 hertz, and the inverted pink triangles are for a vibration frequency of 60 hertz. We see for any given superficial gas velocity, there is a significant improvement in the gas holdup due to low frequency vibrations. But you also note that there are maxima in the gas holdup when operated at the frequencies of 30, 40, and 60. For example, we see at 30 Hertz, there's a maximum in the gas holdup here. The maximum is shifted to a different position at 40 Hertz, and this is the operation at 60 Hertz. If we look at the column at certain positions, say that corresponding to this maximum here, I examine the gas holdup in the column, we see this behavior, whereas if we look at an unvibrated column, we see that the bubbles are larger in size. So applying low frequency vibrations reduces the bubble size and also increases the gas holdup. Without vibrations, the bubbles appear to be larger in size. So we now address the question, why are these maxima observed in the gas holdup versus gas velocity graph? Let's look at two sets of experiments with bubble columns. We first look at the blue line that shows a set of experiments in which the clear liquid in the bubble column, which is water, is 0.97 meters or 97 centimeters. And we plot the gas holdup enhancement. That is, the enhancement, the enhancement is calculated as the gas holdup when the column is vibrated at a certain frequency, and the vibration frequency is plotted on the x-axis. The gas holdup at any given vibration frequency is divided by the gas holdup for the same column that is unvibrated. The superficial gas velocity in these experiments are maintained constant at 4.1 millimeters per second, and the vibration amplitude is 0.3 millimeters. And we note that the gas holdup enhancement is highest at a frequency in this of 24 Hertz, and then it reduces and further shows another maximum at a frequency of about 64 Hertz. And then it decreases. Let's look at the experiments shown by the red line, which are obtained with a clay liquid height of 1.27 meters. Again, we see that there is a maximum in the gas holdup at a frequency little lower than 20 Hertz. And then the enhancement is practically unity. And then at a frequency of 50 Hertz, we can see a maximum. And then it reduces, the enhancement is reduced. And at a frequency of 80 Hertz, we see a gas holdup enhancement of 2.2. So the enhancement is in the gas holdup is highest corresponding to certain vibration frequencies for a given height of liquid. For a liquid height of 97 centimeters, there are two maxima shown here and here at 24 hertz and approximately 60 hertz. For a column in which the water height is 1.27 centimeters, there are three maxima corresponding to a vibration frequency of 20 hertz, 50 hertz, and 80 hertz. I would like to demonstrate in the subsequent slides that these maxima in the gas holdup enhancement correspond to different harmonic modes of bubble column operation. The first maxima corresponds to this harmonic mode of operation. The second maximum, that is for these two cases, corresponds to this harmonic mode of operation. And this third maximum, which is obtained with a liquid height of 1.27 meters, is for a column in which we have the third harmonic. Let's first examine the set of experiments that were carried out for a height of liquid 0.97 meters. The superficial gas velocity is maintained constant at 4.1 millimeters per second. The vibration amplitude is 0.3 millimeters. The gas holdup enhancement with respect to the unvibrated column is plotted as a function of the vibration frequency. We show video recordings of the column operation for a vibration frequency of 0, in other words, an unvibrated column, and a column that corresponds to a vibration frequency of 24 hertz. And we would like to demonstrate that this is the first harmonic for the bubble column operation. And we note another maximum at a vibration frequency of 59 hertz. And we would like to demonstrate that this corresponds to the second harmonic in the bubble column operation. So let's have a look at the three video recordings in turn, starting with an unvibrated column. The gas holdup distribution is practically constant along the column height. So this operation corresponds to this position here. Now we turn our attention to the first maximum that is observed at 24 hertz, and the column operation is shown here. We see there's a higher bubble concentration near the top and a lower concentration of bubbles near the bottom at this position. Now let's look at the operations corresponding to 59 hertz vibration frequency. We see regions of high gas holdups here and here. These correspond to the antinodes and the positions where the gas holdup is lower, correspond to the nodes of the harmonic. We now examine the experiments in which the column height of the clear liquid is maintained at 1.22 meters. The superficial gas velocity is maintained at 4.1 millimeters per second. The vibration amplitude is 0.3. We plot the gas holdup enhancement, i.e. the gas holdup with respect to the holdup of an unvibrated bubble column as a function of the vibration frequency. We note there are 3 maxima corresponding to the 3 harmonic modes of operation. For an unvibrated column, the gas holdup varies uniformly up the column. However, if we look at the column that is vibrated at a frequency of 79 hertz, and we note that the gas holdup distribution in the column is non-uniform. At the nodes, we have a lower gas holdup, but at the antinodes, we have a significantly higher holdup of gas. So you have a low holdup, high holdup, low holdup, high holdup, low holdup, high holdup. So this is the third harmonic for the bubble column operation. We now examine the bubble column operations at the third harmonic in more detail. The local holdups along the height of the column are plotted here as a function of column height, and we see there are low holdup, high holdup, low holdup, high holdup, low holdup. The high holdups correspond to the antinodes, and the low holdups correspond to the nodes of the harmonic. The operation of a unvibrated column is shown in the in this set of symbols with yellow circles, and the gas holdups are practically uniform but significantly lower than the gas holdups obtained for an operation in the third harmonic mode. Let's have a close-up of the column at position corresponding to this antinode here, and the video recordings are shown here. You see practically uniform sized bubbles. At this position, for the operation at the third harmonic, the holdup is significantly lower than the holdup here, and this corresponds to the node of the third harmonic. And if we zoom in to the column, we see far fewer bubbles than at the antinode. So the nodes are more sparsely populated than the antinodes. We compare both of these antinodes and nodes with an unvibrated column, is shown on the left. We see the unvibrated column has significantly larger sized bubbles, and the gas holdup is significantly lower. Due to the sinusoidal waves that traverse the bubble column, the bubbles are subjected to a force that is termed the Bjerknes force. For a wave shown here, the force is directed in this manner, and for this wave, the force is directed downwards. The time average force is non-zero and directed towards the antinode for a column subjected to sinusoidal vibrations. This is explained in detail in my paper. We now investigate the influence of vibrations on the gas-solid fluidization. We consider a Geldart-A powder, porous silica particle of 38 micrometers, and let's look at a column that is operated at a superficial gas velocity of 33 millimeters per second. The column operation for an unvibrated fluidized bed is shown here. And if we zoom in, we can see the bubbles rising to the silica particles. For comparison, let's look at an vibrated column in which the vibration amplitude is 1 millimeter and the vibration frequency is 30 hertz. The video recording of the fluidized bed is shown here. And if we compare that with a unvibrated column, we see there is even visually, we see a higher gas holdup for the vibrated column. If we examine the column in more detail by zooming in, we see that the bubbles appear to be smaller as compared to the unvibrated column. Indeed, in this graph on the right hand side, we plot the bed expansion as a function of superficial velocity for the unvibrated column and the vibrated column, and the vibrated column shows a significantly higher bed expansion. Bubbles are smaller when the bed is vibrated, and the gas holdup is significantly increased. This is for a Geldart-A powder. It is well known that cohesive powders are difficult to fluidize. In the Geldart classification, they are termed C powders. Examples are flour and starch. One way to fluidize cohesive powders is to subject the fluidized bed to low frequency vibrations. I demonstrate that with a video recording that shows wheat flour of 5 micrometer size subjected to a vibration at a frequency of 15 hertz. If the vibration is stopped, then we note that channels are formed and the bed does not fluidize. So an unfluidized bed of C powder results in channeling. And to obtain fluidization, the trick is to vibrate the bed. You notice that as time progresses and the bed is not vibrated, the channeling gets more and more severe. I end this presentation by providing you a list of publications that I have used in preparing the slides that I have shown in the foregoing. They relate to single bubble phenomena and influence of low frequency vibration on bubble columns, fluidized beds, and even on Taylor flow inside monoliths.